Speaker Jon Links from UK, and he'll speak on Yang-Baxter integrability of bosons hopping on the square lattice with global range interaction. Thanks, John.
Thanks, Murray. So I want to start with saying I first met Rodney in 1987. So from 1985 to 1987, I was an undergrad student at ANU. And in 87, I signed up for a Stat Mech course, and Rodney was the lecturer. And the last time I spoke with Rodney, that was in 2023. That was at the Australian and New Zealand Association of Maths Physics conference that was held in Hobart. And Rodney was there to present the Baxter Prize, which had just been initiated in the time preceding that meeting. And so in that interim time between 87 and 2023, I met Rodney on several occasions, several conferences, small conferences like the annual StatMech meetings, some bigger conferences like StatPhys in Cairns. I had the pleasure of introducing Rodney at the AustMS meeting of 2005 that was held at the University of Western Australia. And so our paths crossed many times over the years. I never actually collaborated with Rodney, but I just wanted to start by thanking Vladimir and Murray for the invitation to speak at this meeting. It's a great privilege for me. So to motivate this problem I've been working on, this is a paper from 2016. It's an experimental paper with the title Quantum Phases from Competing Short and Long-Range Interactions in an Optical Lattice. So this is what really motivates this study. So we look at this schematic presentation of the lattice. What we've got is a system of cold rubidium atoms. We've got lasers that are focused in the vertical direction, and they have the effect of trapping these particles into this square lattice structure. And then in the horizontal direction, we've got the effect of what's called an optical cavity. So light shines through the back of the mirror, and then it bounces back between these two mirrors and forms standing waves. And through these standing waves, the atoms can interact by emitting and absorbing photons. And so this is the long range interaction. If you notice here in the caption, they refer to as infinite range at this point here, but later on it's called long range. In the literature, it's also called global range. That's my preference for describing this interaction because the scale of this experiment is like millimeters. So I don't think infinite range is really conveying what's going on, but it's a global range interaction. So through the cavity, we get the atoms interacting with each other across the lattice, and then the vertical interaction, the optical lattice that's caused by the vertical lasers are short range interactions. And then by tuning the frequency and intensity of the lasers, they can control the interactions. Okay, so in this paper, this is the Hamiltonian that they propose to study this system. So the first two lines of the Hamiltonian there, that's the standard Bose-Hubbard model. So you've got hopping terms as first term in the first line, and then the second term there is the on-site interaction. And they use this notation to label the lattice sites as being even or odd. So an important property of the square lattice is it's a bipartite lattice. That's something I'm going to use in my subsequent study of the system. The fact we've got a bipartite lattice turns out to be very important. Okay, so we've got the Bose-Hubbard model. In the second line there, the last term there is chemical potential terms. They write down those terms in the Hamiltonian, but they don't ever actually discuss them through the paper. The main focus is on the competition between this first term in the second line and the terms in the first line. So this is this interaction term is what's due to the cavity, and we see that it's quite a simple form. It's just the sum of the number of operators on the even sites minus those on the odd sites, and then you take the square of that. Okay, so if I was just looking at the Bose-Hubbard model, well, in a one-dimensional system, that's largely considered to not be a solvable model. So there's very little chance of solving that in 2 dimensions. But if we ignore this second term here with the US coupling and just look at the hopping term and this cavity interaction term, then what I'm hoping to convince you today is that that's an integrable model in 2 dimensions. So of course, free bosons, we can solve in 2 dimensions. That can be done very straightforward using basic properties of linear algebra. We don't need anything like Yang-Baxter. But if I incorporate this interaction here, then I can apply a Yang-Baxter process to derive conserved operators and arrive at a beta ansatz solution. So that's my goal. So next up, I've got this quotation. So we've seen this earlier in the week. There's Professor Saleur that brought this quotation to his talk. And it goes, there are down-to-earth physicists and chemists who reject lattice models as being unrealistic. In its most extreme form, their argument is that if a model can be solved exactly, then it must be pathological. I think this is defeatist nonsense. So I can't solve that full model that was presented on the previous page. But if I ignore the on-site interactions and the chemical potential term and just take the hopping terms and the global range interaction that comes from the cavity, then I can do something with that. Okay, so to get us there, I'm going to start off with just a discussion of free bosons. It's fairly elementary, but just to make sure everyone's sort of on the same page, let's consider free bosons on the square lattice with open boundary conditions. So I've got a representative there of a square lattice, just a 4x4 lattice. It's a bipartite lattice. That means I can label or color rather each one of the vertices with a red or a blue in such a way that red sites only have blue neighbors and vice versa. And the way to set this up is through the use of an adjacency matrix. So we can formulate that in the following way. If I take this square lattice, 4x4 square lattice I've got here, and think of this in graph theoretic terms, then a graph is defined by its vertex set and the edges between the vertices. So if I just redraw the square lattice in this picture on the right-hand side here, well, what I've done is I've just taken the blue vertices and I've labeled them starting here. This is 1, 2, 3, 4, 4, 5, 6, 7, and 8. And then just reflect that for the red. So this is 1 for the red, and this is the 8 for the red. And then if there's a connection between the vertices, you draw a line, and if there's not, you leave it blank. And then you can just read off from this picture on the right-hand side here what the adjacency matrix is. So So in this particular case, there's no edge between the first blue and the first red. So that means that the 1, 1 entry of the matrix is 0. But then we see we have a 1 in the 1, 2 and the 2, 1 positions. And you go through and you fill in this matrix B. That's what I'm calling B. And then the full adjacency matrix for the system is of this form here. And if we do a transformation on this matrix, we can bring it into this form. We've got B in the top block and minus B in the second block. So that's just telling us that the eigenvalues of the adjacency matrix A is just the union of the matrix, the eigenvalues for B with those for minus B. Okay, so that's the open boundary condition situation. All right, so now we write down a Hamiltonian for this. I'm going to use 2 sets of operators, one AJs and the other BJs, just to encode that bipartite nature. And then we have that the free boson Hamiltonian is the one that's shown here. So we get particles of B type, hopping into neighboring sites and becoming A-type and vice versa. Okay, so this is very straightforward to analyze. We can write down simple expressions for the conserved operators. They're just expressed in terms of these matrix powers in B. So B to the 2p there, that's just the matrix power of the matrix B, and then we take the jkth entry and we create these C2p's and 2p plus 1 in the following way. And it's very straightforward to do a calculation to show that they commute. Okay, if I want to change boundary conditions. So I want to go to cylindrical boundary conditions. So now I'm going to take those vertex sites at the top of the lattice and connect them to the bottom. So that's represented here by the dashed lines. That means I just add an extra 4 edges to the system, and there's going to be an extra 4 ones in the adjacency matrix, or in the matrix B. You can see here that the site labeled 1, well, it's very sensitive. The site labeled 1 now connects to the site labeled 7 through this imposition of the cylindrical boundary condition. So we get some extra entries in the matrix. And then we go to the torus. So we join up the vertical sides and we put fully periodic boundary conditions. Then that changes our adjacency matrix by adding in some more edges. But the key point that I want to emphasize here is that we can change these boundary conditions for the system just by changing the adjacency matrix. So in going from open boundaries to periodic boundary conditions, in this approach that I'm taking, there's no sense of needing to use reflection equations or anything like that. It's all just encoded into the adjacency matrix of the system. So then if we want to know what the spectrum is for the free boson system, then we just need to diagonalize the adjacency matrix. And this is a well-known result. So for open boundary conditions, we have that the form is given by the first expression there, and then for cylindrical and the toroidal boundary conditions, we have the subsequent forms. So for the square lattice, it's very special because you take the adjacency matrix for the square lattice, and then you can write that as a sum of 2 matrices, one that just encodes the connections or the edges that go vertically, and the other with the edges that go horizontally. And then those 2 matrices commute. So you can diagonalize them simultaneously, but each matrix is just describing a collection of one-dimensional systems. And you just use standard techniques to diagonalize the one-dimensional systems, and that's why you get these familiar formulae for the single quasi-particle energies in the free boson case. All right, so now what I want to go to the interacting system. So what I'm going to do is just take the same system and add in this term here, which is this global range interaction due to the cavity. So it's just a simple difference of the NA with the MB and take the square of that. Okay, so first of all, I'm just going to show you what the conserved operators are for this system. So, and then I'm going to show you where they come from. So we see that when you include this interaction, that when we have conserved operators depending on an even variable here, it's exactly the same as in the free case. There's no change. But when we have the odd case, then we get this extra term here with the coupling U. So as U goes to 0, this just reverts back to the free boson case. And the term with coupling U is given by this expression here. So in the free boson case, we've got conserved operators which are quadratic in the boson operators. And then once we include the interaction, then we get these 4th order terms appearing in the conserved operators. But these are the conserved operators made fully explicit. We're not using any type of boost procedure, which is common in one-dimensional spin chains, where you can, in theory, generate the conserved operators, but in practice, once the number of times you have to apply that iteratively, it becomes prohibitive to write down explicit expressions. But here we can get all the expressions explicitly for the conserved operators. Okay, so how did we get to these expressions? So the approach I'm taking here is quite different from what people might be familiar with in setting up integrable systems with a Yang-Baxter equation. I'm working with the classical Yang-Baxter equation. And what I'm going to do is I'm going to set up a system of relations in a Poisson algebra. So here's my R matrix. So it's an operator acting on a twofold tensor product space. And the classical Yang-Baxter equation, which is essentially what you'll get by linearizing the regular quantum Yang-Baxter equation, has this form that's shown in the second line here. There's a slight difference in the sense that commonly you'll see this equation where this second term here has a plus sign and this R21 is replaced with an R12. That's in the cases where you have what's called skew symmetry, the R matrix, but we don't have that here. So this is the one that will preserve the anti-symmetry of the Poisson bracket. So given this solution of the classical Yang-Baxter equation, you can define a Poisson algebra with generating functions tjk, depending on a parameter u, and then the Poisson bracket is encoded in this way here. Okay. Now with this Poisson algebra approach, it's also quite common to use what's known as a shift operator. So that's a matrix B which satisfies this equation that's shown here. And then what I'm going to do is realize the Poisson algebra through the dual of GLN. So GLN's the familiar Lie algebra. We take the dual of that and we can endow that with a Poisson bracket structure, which is just the same structure of the relations in the GLN Lie algebra. So when we do that, that allows us to set up this homomorphism from the TJKs to these elements in the Poisson algebra, and we've got some constant term that leads here. Then what we do is we define here the T2 and recursively define TR plus 1 through this definition here. So basically this is just defining matrix powers of the T's, but these T's here, these are not operators on a vector space, these are functions because we're dealing with a Poisson algebra. So when we take the trace of these objects here, we get this expression here. These are the analogues of the transfer matrix, but they're not matrices, but they do the job of transfer matrices in that they provide functions which commute with respect to the Poisson bracket. So what I'm doing here is actually considering what are analogues of higher order transfer matrices. So this index, the R and the S here, refers to higher order cases. So in a spin chain situation, you get higher order transfer matrices by undertaking fusion in the auxiliary space. So these are the analogues of those. And then if I undertake this process, I can do an expansion of these in the variable u, and then all the coefficients here will give me Poisson commuting functions. This generates a lot of functions. They're not all independent. We don't need all of them. We just have to identify the relevant ones. Okay, so once I've set this up in this Poisson algebra structure, what I need to do is then do a mapping towards a Lie algebra, which in this case here will be the universal enveloping algebra of GLN. So the way that we map this is basically through this sort of Jordan product form. So we consider the Poisson algebra as being like a polynomial algebra, and for each homogeneous polynomial in the algebra, then you can take its expression like this and then map it to an element in the universal enveloping algebra. So basically, we just do the direct thing here where we have the Poisson basis elements mapping to the typical basis elements in the GLN algebra. But then you just completely symmetrize it. Because you've got commutativity of the calligraphic x's that appear here, so that's intrinsically a symmetric expression, then you make this symmetric just by taking this sum and applying the symmetric group action to the indices. And then you extend that to the whole of the system. So in this way, you get a mapping from the polynomial algebra into the the universal enveloping algebra of GLN. So basically, this is a different way of working in the enveloping algebra compared to the PBW basis, which is the usual thing that people might do, use these Jordan products. Oh, I should say that in itself won't guarantee that I get commutativity of the when I map the Poisson commuting elements into the Lie algebra. That in itself doesn't guarantee that they'll commute. There's still an extra step that needs to be taken. But now I need to make this concrete. I need to give you a specific R matrix to work with. So here's the R matrix I'm going to take. Solves the classical Yang-Baxter equation. So if you just take this ansatz, we've got a permutation operator here, and then A is just an arbitrary operator on Cn. And then you just put that into the classical Yang-Baxter equation. You see that that will hold provided A squared is equal to the identity. And then we look to the shift operator equation. The shift operator equation assume this ansatz for B, that it's just the parameter U times some other matrix B, and put that into this equation here. And then we get the simple condition that A and B must anti-commute. Okay, so A squared is equal to I, B must anti-commute, and this can be easily satisfied in a number of ways, but what we do here is just express this in terms of a tensor product. So the space Cn, we set M to be equal to N over 2, and so we've got this identity here in this matrix B acting on the Cm space, and we take a tensor with Pauli matrices, and then these two conditions are automatically satisfied without any condition on this matrix B. B is arbitrary here. Okay, so just to run through the setup. So what we've got here is that we take the R matrix from the earlier slide. The U parameter that comes into the system is related to the V through this relation here. Then you construct these analogues of transfer matrices in the Poisson algebra, and in the expansion, we just take these particular cases here. These are the quadratic and the linear terms in these calligraphic E's. And then to show that they actually commute when we map them into the universal enveloping algebra, we use the approach that's taken by Winberg, a paper we found that was published in 1991. And basically what Winberg does is to define some involutions and anti-involutions on the algebra and just use properties of those involutions and anti-involutions to deduce that when you perform this mapping from your Poisson elements into the enveloping algebra through that Jordan product form, that it does guarantee that you've got commutativity. So you've got a commutative subalgebra in the enveloping algebra of GLN. And then the last step is to map those to bosons through the typical Jordan-Schwinger type of mapping. So because of the bipartite structure, we can implement that by identifying odd indices with the A operators and even ones with the B operators. And when you do that, that's the final answer. You get that these operators expressed here form commuting set. So given that we've got a Hamiltonian, and so the Hamiltonian, I should say, occurs from this expression here when P is equal to 0. When P is equal to 0 in the first expression there, that's just your number operator. You've got conservation of particle number. P equals 0 in this second expression here, or in other words, C1, that's the Hamiltonian, and then we've got the higher order conserved operators for other values of P. All right, so in the time remaining, just say something about the beta ansatz. So if we've got a solution, we've got a system that we're claiming to be integrable, then we should hope to be able to find some beta ansatz solution for it. The way that we do this is just by mapping this system to another system and then using the fact that we can describe the beta ansatz solution for that other system that we've mapped to. So the key here really is to work in an eigenbasis for the matrix B. Okay, so if we diagonalize B through the introduction of these X matrices and their daggers, we have this expression here. These calligraphic E's here are the eigenvalues now. They're not distinct from the Poisson elements that I introduced earlier. These are the eigenvalues of the matrix B. And then when I apply that mapping to the Hamiltonian, it has this very special property that the first interaction term here is invariant. Okay, so the number operator for A's under this transformation that's introduced here just becomes an number operator for C type bosons, and likewise the number operator for B and D type bosons are equal. So the transformation leaves the first term invariant and it just diagonalizes the second term. And so what it does is, in the second term now, we've got hoppings in this transform space where for each level J, the number is conserved. So there's no sort of off-diagonal terms now. We've diagonalized the matrix. So these are conserved operators, these NJs, which are just the number operator of C-type particles at level J plus the number operator for the D-type particles at level J. And then the sum of those is the total particle number for the system. So for this Hamiltonian that I've introduced here, we can go to the literature and find the beta ansatz results. So you pick a set of quantum numbers for those number operators and then construct this reference state. So you take the D-type particles from 1 to m and then raise them to the powers of the NJs. And then you find that the beta ansatz solution is described in terms of these equations here for the beta roots. And if we stick them into the energy expression here, that gives us a spectrum of the interacting system, and the beta states appear at the bottom here. So we've got these creation operators, the C's acting on these pseudo vacuum states given by these expressions here. Okay, so that's the beta ansatz solution for the system. So just to summarize, so motivated by the optical lattice setup in the cavity that I introduced at the very start of the talk, I'm considering this system of 3 bosons on the square lattice and then introducing into that a global range interaction. Found that this Hamiltonian with the interaction still emits conserved operators, and we can find a beta ansatz solution and explicit forms for the conserved operators through using classical Yang-Baxter equation approach applied to a Poisson structure and then basically quantizing that Poisson structure. We can undertake this for different boundary conditions. They just get, the different boundary conditions just get encoded into the adjacency matrix, and this procedure will work for general bipartite graphs. So for example, if I want to apply this to a honeycomb lattice, it will also work. And just to conclude, there's a couple of papers recently put on the archive with some of the details. The beta ansatz solution has been developed in the full algebraic form in this paper by Taras Skripnik from 2023. The model that we're considering here is just a limiting case of this general elliptic Gaussian system that Taras has analyzed. It's a very technical calculation because of the lack of U1 symmetry in the elliptic case. The experimental paper here, details for that from 2016 are shown, and then this paper by Winberg, which was very helpful for us to complete the argument from 1991, is the reference for that is given there. So thanks for your attention.
Hey, John, do you have any questions there from online? Vladimir has a question here.
Yes, actually 2 questions. The interaction part of the Hamiltonian is just square of the sum of the square of the difference of number operator for all sides of the chain.
Yep.
Can you show the second last transparency again? Okay. Or the third? Yeah.
That one?
Oh, before,
Before.
I think.
The Hamiltonian.
Yeah.
This is the transformed Hamiltonian here.
Yes.
So it's not free fermion. Yeah, that's clear.
No, that first term doesn't commute with the second term
Yeah.
because of the square.
And you don't have obviously Yang-Baxter, quantum Yang-Baxter equation. Because
Sorry,
it,
I don't.
because it's not local. Yes.
No, it's not local. No, this is long range, global range. It's highly non-local. That's correct.
And the interaction doesn't decay.
Sorry, the interaction.
Does not decay with the distance.
No, it's not like Haldane-Shaftesbury. No, that's why I call it global range. So all the particles, it doesn't matter where they are in the lattice, the effect of the interaction between blue sites and red sites is the same. It's independent of where they actually sit in the square lattice.
We don't think we have any further questions, John, so thanks again for a nice talk.